figure into it. Oh, I'm not question.
Okay, let's go ahead and get started. I got one question which I would like to answer at the beginning of class because I think we can do this already. And this is 1.4 on the homework. And so this one's not mathematically, it's not hard, but just getting your head around it might take just a little bit of picture. All right, so 1.4 reads as follows. A driver in a blue car traveling at 50 kilometers per hour sees a red car approaching in his rear view mirror. So let's draw a little road. Draw a picture of this. So it says that the blue car is traveling, he sees the red car in his rear view mirror. So I'm going to label this as the blue car. Write the velocity in the x direction of the blue car as vbx, and that's 50 kilometers per hour. You'll probably want to rewrite that in meters per second. And when you do that, that's an exercise for you. And he sees a red car approaching in his rear view mirror. V red x. And that red car is going 60 kilometers per hour. Okay. And the question is, okay, how long does it take for the red car to pass the blue car? And then in that time, how far did they travel? The distance between these two, the front of the red car and the front of the blue car, I assume, was 30 meters. So, if we think about this a little bit, this is a chapter for the kinematics, and that's a clue. Remember we have these kinematic equations, that x at any time is equal to the initial x position of an object plus the initial velocity in the x direction times time, plus 1/2 times the acceleration in the x direction times the square of the time. This assumes constant acceleration, or a constant rate of change of velocity. All right. In this one, if they're going at a constant speed in the x direction, what's the acceleration?
Constant acceleration is not accelerating, maintaining speed. You're not slowing down, you're not going forward.
Good. So so what's acceleration?
Zero.
Zero, right? Okay. So if the acceleration's the change in the velocity. So if it's not changing, it's zero. Rate of change of velocity. So in our case, the acceleration of both of these, 0. So I could write the x position of each of these cars. And when they pass each other, that x position should be 0, or should be equal to each other, shouldn't it? So when they're passing each other, that x position will be the same for both those cars. So I'm going to start measuring x equals 0 here at time t equals 0. So that the initial position of the red car would be 0. And the initial position of the blue car would be 30 meters. Okay. And I'm going to start just plugging things in here. So the position of the red car at any time is going to be just the velocity of the red car times time. That makes sense?
What is that?
Acceleration 0, initial position 0.
What's the XR?
Oh, this would be the x position of the red car. that make sense? I just plug things in here. I'm looking at the position of the red car. The initial position 0. You have an initial velocity in the x direction times time. This is 0. So that equation becomes this. What's the x position of the blue car? What's it? Yeah, it'd be 30 meters is the initial x position plus
Initial velocity of the blue car.
the initial velocity of the blue car in the x direction times time. Okay. And then just set those two equal to each other, and that's what's happened. And since they'll be equal to each other when they're passing. So I'd get initial velocity in the x direction times time of the red car is going to be equal to 30 meters plus the initial velocity of the blue car in the x direction times time. This is my condition. This will give me the time when they pass. Set their positions equal to each other right here. And and if I solve for that time, that'll be the time that they pass each other. And that's fairly straightforward, and it'll give you exactly what you expect. The initial velocity in the r direction times time. I'm going to subtract both sides. Blue car in the x direction times time is equal to 30 meters. Or the initial velocity in the r direction minus initial velocity in the blue car, the x direction times time is 30 meters. So the difference in velocities times time is equal to the difference in positions of the cars. You could almost have guessed that if you were just going to try and do this without these equations. You know that if you're on a car, if the car behind you is going 5 miles an hour quicker than you, that it's catching up with you at a rate of 5 miles an hour. You see that this is the difference in velocities of those cars. This is the rate at which one car is catching up with the other car. Anyway, solve for the time here. So this time would be at 30 meters divided by initial velocity of the red car minus initial velocity of the blue car. I'm dropping the x because we're only in one direction here. And that would be the time. The second part of this problem asks you, okay, how far did the blue car travel in that time? So I want to see the difference between its initial position and final position of the blue car. So the distance it traveled would be the time minus the initial position which would be the same thing as the position of the blue car minus that initial 30 meters. And we see that from this equation that it's just the velocity of the blue car times the time. Well, the time that we're talking about is the time for the overtaking, which was just this time. So I can plug that in. So that would be times 30 meters over velocity of the red car minus velocity of the blue car. This is 50 kilometers per hour. 60 minus 50 kilometers per hour. So that would be 50 kilometers per hour. This is 10 kilometers per hour times 30 meters. You see what I did here? So this is 10 kilometers per hour, 50 kilometers per hour. So I just took this 10, multiplied it. I could write it like this.
What about the other side of the equation?
That's the distance. That's what we're trying to solve for.
Oh, okay. That's it.
This is the distance traveled. And so this is just 5 times 30 meters, which is 150 meters. We don't know this would be.
Oh,
Okay.
that's just because acceleration is 0, right?
Yeah.
Okay.
Acceleration 0, so that
So that
equation becomes
cancels out.
straightforward.
Okay.
Make sense?
So
Yes.
on problems like that, would we have to change the units of the velocity and
For-
then solve for time?
No, for the time, yes.
Yes. Okay.
For this part, notice that we got, because we did everything algebraically and then substituted things in. And everything was in a ratio, so the units canceled out. But I can get the distance without ever converting units.
Well,
So that made it a lot easier.
I don't see you got.
well, those are kilometers over hour, and that's 30 meters.
Yeah. So we have,
So you just did times 5, right?
so I have a ratio of 30 kilometers per hour. That was the
Oh.
velocity in the blue. The difference in velocities was 10 kilometers per hour.
Okay.
The units actually cancel.
Oh, sure. Yeah. So it's just 5.
And I just
times
have
30.
5 times 30,
Gotcha.
or 50.
How do you get? It has with the velocity initial on the blue car, and it has 30 meters over the that right there. Wouldn't it be 30 over 10? How does it get to the 50 over 10?
Okay, so I have 50 kilometers per hour. By the way, it writes up per hour like that. 30 meters over 10 kilometers per hour. This is the same thing as 50 kilometers per hour over 10 kilometers per hour times 30 meters. All we're doing is we're doing the division by 10 first rather than second. But the order of operations for multiplication and division, you can reverse that order, okay? That make sense? All right. Yes.
The XB in the parentheses, is that a D or a T?
X.
Up top, the very first.
This one?
Yeah.
B.
T.
No.
Oh, T. This is the X position of the blue car at a time T, not at T, at a time T. Okay. All right. Are you guys good or sort of?
I'm 30 meters off.
What's that?
I came up with 180, so someplace on
Well, you'd
that
have to
might
add
go
over
to
the
Well, that would
30
be
meters.
the X position would be 180 meters from 0. But but it started out at 30 meters, and the question was, what's the distance it traveled in that time?
Yeah.
So that would be the difference
The
from.
D travel. Car, blue traveling before red after the car.
So you have to subtract the initial position from that because the distance it traveled is the distance from here to its position over here at that time.
D has moved X meters.
No.
R has moved X three.
No. B moved. B moved. The X position would be 180 meters for B at the end of it all. But it started out at 30 meters. So the amount it moved is at 180 meters minus that 30 meters.
He's saying, like, imagine if it's a coordinate plane and the front of R is the origin.
The red cars have moved X plus 30, and the blue has had moved X.
No, the blue, we're saying the red moved X. Okay, because it starts out
But
as,
by doing it, either way, you ought to come up with the same answer.
and you will, 150 meters.
That's what I say, somewhere I've got my 30 in there again, and I shouldn't.
Okay.
You should be able to do it as either X plus 30 or X minus 30. Set your equation up, you ought to come up with the same.
Start out with a coordinate system. Whatever you want to call the X equals 0, that's fine. Call this X equals 0, and then the initial X position of R would be minus 30. Okay? But I started it out here, and then the initial X position of the B is plus 30. I think it'll work out either way.
Just gotta sharpen my pencil. Clean my eraser.
On 3, can you I don't know how to do it, but can you explain what it's asking for? 1.3.
Okay, that was a lot like the Bugatti Veyron on the on-ramp problem. This one says a jogger starting their morning run accelerates from a standstill to their steady jogging pace of 8 kilometers per hour. They reach a speed of 8 kilometers per hour 5 seconds after starting. How long does it take the jogger to reach the end of their 20-meter driveway? Okay, so this actually is a two-part problem, a little bit more complicated than the Bugatti Veyron one. Okay, so imagine I have a runner, which I'm going to represent as a box. Yes?
What number is the problem?
This is number 3. And it starts out X equals 0 at T equals 0. Okay? The runner accelerates for 5 seconds. And at 5 seconds, let me just represent this as an X. I don't know what position this is, but at 5 seconds, they move at a constant speed after this. So there's an acceleration up until this point. Then at this point, there's no longer any acceleration. And so for the remaining, and they're moving at a speed of 8 kilometers per hour. And we want to see how long it took to get to X equals 20 meters.
If it doesn't tell you where it's going, is it technically a velocity, like the direction?
Yeah, I'm assuming that the driveway is straight in the X direction. Okay. So we'll say the coordinates along the driveway. X is along the driveway. Okay. So let's figure out how far it traveled in that time. In the first 5 seconds. And then we'll know how far it had to travel in this time. Okay? And then we'll be able to get the total amount of time it took to go to the 20 meters.
So would that be finding displacement?
Yeah.
Okay.
So here it starts out so I'm going to write my equation. X at any time when I have an acceleration would be the initial X position plus the initial velocity in the X direction times time plus 1/2 acceleration in the X direction times the square of the time. Now, if it starts out at X equals 0, what's the initial X position? 0. And if it starts out at 0 speed, what would be the initial X velocity? 0. So I get X at 5 seconds. I want to figure out at 5 seconds. It's going to be 1/2 acceleration, the X direction, times time squared, which would be 5 seconds. squared. I guess I want to get what the acceleration was from this. So well, actually I have two things I don't know. I don't know the acceleration and I don't know what the x is. I need to get both. All right, so I have to figure out what the acceleration was. We have a clue. We know that the final speed it got up to was 8 kilometers per hour.
Minus the initial to 0.
Yeah. So I can say that the acceleration in the x direction would be the final speed. I'm going to put a little bf here. Minus 0 kilometers per hour over the time it took. It was 5 seconds. So if I plug in numbers here, well, I'd have to put in the 8 kilometers per hour, but I want to make that into meters per second divided by the 5 seconds.
0.44. So I changed the 8 kilometers per hour
You'll want to, yeah, so
to
you want
meters per
to,
second, which is 2.22 meters per second, and then divided it by 5.
should we go through the conversion from kilometers per hour to meters per second? So 8 kilometers per hour. I'm going to write that kilometers per hour. It's the same, and I'm going to multiply by 1 until I get to meters per second, but I'm going to write 1 as 1,000 meters. Same thing as 1 kilometer. And then this would cancel out the kilometer unit here. That's how I knew how to write it. And then what's 1 hour in terms of in seconds?
3,600.
I want the seconds on the bottom. So 3,600 seconds is 1 hour. Then the hours will cancel. And so I'll get 8,000 divided by 3,600, and it was
2.22.
2.22 meters per second. Okay, so I write this as 2.22 meters per second divided by 5 seconds. And what's that equal to?
I got 0.444.
0.
4 zeros. 4. That's what I got in my calculator.
Meters per second squared. So that's the acceleration in the x direction. Make sense? So go ahead with that number, plug that into here. So I get x at 5 seconds is 1/2 times 0.44 meters per second squared times 5 seconds squared. And if I multiply that out, what do you get? So this is 5.5?
Yes.
5.5 meters. So this 5.5 meters at 5 seconds.
Divided by 5. Oh, okay.
Okay, so you first, so he's at 5.5 meters at 5 seconds. And then he's traveling with this, we'll write that as the 2.2 meters per second. The 8 kilometers per hour is 2.2 meters per second. And he has to go from 5.5 meters to 20 meters, and he's traveling with this constant speed. So how far, what's the distance of this?
14.5 meters.
Yeah. 20 minus 5.5, right?
Yeah, so this would be 14.5 meters. Okay. So how long does it take to travel 14.5 meters at a constant speed of 2.22 meters per second?
14.5 divided by 2. 6.5.
It's 2.22 times the time. And there's probably more other ways to do this too, but this is the way I'm doing it now. So, and if I solve for the time, what would I get?
6.5.
Okay, so The time to go from here to here, 6.5 seconds. So the time to start at this point was 5 seconds from when I started. So what's the total time it took from here to here?
6.5 plus the 5.5.
Plus the 5 seconds. So it'd be 11.5 seconds, right? And that's the that's the answer. So the real key is to start out with an understanding of the problem. Try and draw a little picture. Once you understand the problem, how to approach it becomes a lot clearer. Any questions? Yeah.
In the original, the reason you got rid of the x initial is because it was 0, and the reason you got rid of the velocity initial is because it was 0.
Yeah. That's right. And just leave those off. It's no point in keeping them. All right, let's go ahead and we'll do some more kinematics. So this might be a good time to restart in seconds.